the introduction last. Best I can. Thank you so much for so many people turning up. This is amazing. Really look forward to giving the talk. Titled Doomed to Repeat the Past.
Yes.
So this is not about quantum breaking and making your life horrible. It's about you making my life horrible. So this is hardware exploits for quantum computers. So, I'm Jamie Friel. I'm a software engineer at Oxford Quantum Circuits. My main responsibility is within the compiler. So think about runtimes and how runtimes might go wrong. At OQC, we make superconducting quantum computers. We build the full stack as the QPU, the chip itself. We don't build this fridge, the students we don't build. The control hardware, the compilation stack, and then the cloud layer, which is just the most common access point to quantum computers. If you want a rundown on this, I gave a talk last year that sort of compared this to classical control stack. Very loosely, we have a CPU, we have a motherboard, and we have a compiler and a runtime, and then a cloud layer. That's how to think of these. I try to relate this to classical concepts as much as I can. It's meant to be open and bridge the gap between quantum and security, so please raise your hand if you have questions throughout. I want it to be clear to everyone. So we do at OQC, we build quantum computers. It's available on AWS, privately through cloud. The reason I want to give this talk is that quantum computers will solve many great problems, not just cracking encryption and all that stuff. Many good things, drug discovery, simulated molecules, machine learning, optimization problems, logistics. All of that is very, very sensitive data. All of that is data that if it was leaked, I'd be in big trouble. And so we're starting the work now to make sure our environments are secure so that when we get to solving real problems, we know we're not going to have things like Zenbleed and Downfall, which turned up a few days ago. I don't know if anyone has been involved in patching this. My heart goes out to you. If anyone had to patch Meltdown or Spectre again, my heart goes out to you. It will be me one day. Hardware exploits are still a big problem. Complex CPU optimizations give rise to complex exploits. Very hard to properly secure a complex CPU environment, especially with regards to separating out user space and the system space and privileged information. Right off the back of a big one for people, there are two exploits here. I think one is fixed and the same as the other updates. I don't know if the other one's patched yet, but at least one is. Q-Day is coming for you, for all of you. Q-Day is the day that quantum computers crack encryption, the internet will collapse, Satoshi's sacred bitcoins are stolen. But all of your 1997 PGP emails are free for everyone to read. But it's coming for me sooner. And this is the point of this talk. This will happen, but let's not be hyperbolic about it. This is a very, very long way off. And the solutions to solving the problems of encryption are much further advanced than the quantum computing hardware is. We've got some talks from the folks at Sandbox, are working on post-quantum cryptography, and it's going very well. Looks great. Lattice-based solutions look great. We're redefining a model of computing. We're redefining a runtime environment. We've got many, many more ways to go wrong before we're a risk to anyone. But before we can go into that, primer on quantum computing. This is a NOT gate. I'm sure people are familiar with that. 0 goes to 1 and 1 goes to 0 as input and output. I'm using this weird notation. This is called bracket notation. I'm putting it there so people are comfortable with it. If you go to the literature, it will be there. It doesn't really matter what it is. It's an abstraction to a vector. But I'm just wrapping bits in these things so people are more comfortable with it. And you see, these are just bits right now. There'll be some sources for more information on these gates. But Pauli X. Everything in physics is named after dead old men, which is very useful. This is just a NOT gate. Pauli X. Hadamard, another dead old man. They're all brilliant, to be fair. But this is where we start to get quantum.
Still dead.
Still dead. Hadamard operation on 0, so the 0 bit, this is where you go from a mixture, superposition of 0 or 1. So this is just say it's a 50% probability that when you measure your quantum system, you get 0, 50% of the time you get 1. So this is a coin flip, basically. That's how you think this. This is a coin flip generator, this Hadamard gate. It will go backwards as well. So if you start with this equal superposition state, it will take you back to just 0. So this is a bit more quantum. This is where you have this idea that you can be in 0 and 1 at the same time, and you can do, this is part of where quantum power comes from. You could act on both at the same time. Now if you do this and then a not, you've done a not in both. So again, but there's two 1-bit operations. So I'm ignoring jargon qubits. These are, right now, these are bits. In quantum land, they are qubits. It's a quantum bit. The next step is 2-bit operations. This is C0, or an XOR with a carry. So this is, quantum computation is reversible, so you have to add the X carry. The XOR is if your first bit is 0, do nothing to the second. If your first bit is 1, then do an X gate or a NOT gate on the second bit. This in of itself is, again, this is classical. This is an XOR gate. This is a classical circuit. There's nothing quantum about this necessarily as it's presented yet. We'll see how the combination of this superposition and the C0 become quantum. But those are some classical operations, a little bit of quantum, to understand how we do some computation. Bit level we're at. This is, when we say we have an 8 qubits machine, that's not like an 8-bit computer, we have an 8-bit register, that's like 8 transistors. We are on the bit level of operation for these devices. So this is where we start to get into what a threat model might look like. And is how is it, do we actually do this? How do we make this operation happen? When this is a representation of our device Lucy, 8 qubits connected in a ring. And this is a piece of superconducting material that sits in the bottom of a dilution refrigerator with some wires connected to it. How do we actually do anything with this? So one thing to understand, we're going to brush over the physics here. If anyone wants to talk more about the details, please come talk to me. I'm here all weekend. Always happy to go into more detail on this. We have a frequency associated with each qubit. This frequency is, think of it like an energy, a voltage. If classically your bits are separated by 5 volts, every bit here is separated by a different voltage. This might be a 4 volt difference between 0 and 1, this might be a 3 volt, this maybe is 5 volt. That's what we add that energy into the system to drive the transition from 0 to 1. It happens to be microwave, typically around 5 gigahertz for devices like myself, OQCs and IBMs, Rigettis, around 5 gigahertz. So we add enough energy to pump up from 0 to the 1 state. That's how we do a NOT operation. As I say, just to get the sense, it's the same as adding 5 volt, 4 volt into a system to flip a bit. Now, how do we do the C0 gate? Now, this is a much more subtle operation, and in some regard, you just have to trust me. Sorry, I didn't want to go into the maths of this. It's a bit gnarly. But let's take this example where our X, since our input is qubit 8 and qubit 1. So if qubit 8's in 0, do nothing to qubit 1. If it's in state 1, flip it. The way that I do that is I drive qubit 8 with the energy of qubit 1. And that looks like that should do nothing, right? I'm just driving qubit 8. is this little arm here, is this coupling. We engineer a coupling between the different bits such that when I drive one qubit at the energy of another, it does this operation. So this is how we do 2-bit or 2-qubit operations on a quantum device. So, an example. This is called a Bell test, or G and Z state. Lots of physicist names in that. Start with Hadamard. Let's break it down. This is the first qubit, that's this rail. This is the second qubit, that's this rail here. What does this represent? This is saying that if I take a measurement of my system, because quantum systems collapse into some classical measurement when I measure them, on this first qubit, it's a coin flip. So this is going to be 0 or 1 with equal probability. This bottom rail is always going to be 0. So this is a coin flip, and this is stuck on heads. Another way to represent this is a slightly more compact notation. First qubit, second qubit. First qubit, second qubit. So again, we can see this first one, 0 or 1. Regardless of that outcome, the second qubit is in 0. So this next bit. So remember this, if we're in 0, do nothing. So nothing happens to this part of the quantum state. If the first bit's 0, leave it, do nothing. But the second, the other part of our superposition, the first bit was 1. So we do a flip on this part of the superposition. But what does this mean? Why is this even an important example that I'm belaboring so heavily? We've got 2 coin flippers who are physically distinct from one another. Both flip a coin and hide it. You get heads, immediately you have heads as well. Flip a coin again. You get tails, immediately you have tails as well. There is this correlation between physically distinct bodies that is not possible classically. So they are in lockstep. They are random until you look at one of them, and the other flips into place and agrees with the other. Now we clear, this is not fast and light transmission of data. It's not possible, because this is random. You're just generating random data, but there's just a connection between people that is distant. This is how you combine that superposition and these 2-bit operations to make something that is quantum. This is not possible classically to have this level of correlation between physically distinct entities. So this is hello world in quantum. So this is going to be our test case. We're going to work with. And here's just an example output. So when you do a quantum computation, you repeat the computation many, many times, and you measure it every time, and you get a different classical output. So this is, you see, when the first one's 0, 0, 0, 0, 1, and 1. 0 is not the same. That's the quantum bit. We're going to briefly touch. I'm not a security person. Let me get that out there now. So if anything sounds a bit dubious to you here, it's because it is. But last year at DEF CON, so this is one thing I love about Quantum Village. Last year at DEF CON, it wasn't just us, saying, hey, this is what quantum is. We spent a lot of time talking with red teamers and hardware hackers, teaching me, a quantum information theorist, about the world of security and threat modeling and hardware hacking, all this stuff. And so now we're trying to bring these two worlds together. So everyone in this room, if you do hardware hacking, this is probably painfully simple and oversimplistic. Same for the quantum bit. So a quantum Q specialist, what I said was objectively wrong, probably to them. But you take simple ideas in 2 distinct fields, and you have federal funding for interdisciplinary study. So this is what we're doing here. We're bringing simple ideas from quantum and simple ideas from security and bringing them together to do some really cool things. So Rowhammer. This is a block of DRAM. These are cells that contain data. There is some very, very loose coupling between these cells. There are straight electromagnetic fields. These things are very, very small. But unlike the coupling that we generate in a quantum computer, which is very distinct, very deliberate, this is an accident. This is a byproduct of the fact that you can't perfectly contain these stray fields. So let's say that this is Alice's data in the purple. If Eve, some malicious actor, comes in and starts flipping bits very, very rapidly on either side of Alice's data, you can induce bit flips through this very, very loose coupling. So you have to drive it very, very hard and very precisely. But Google's Project Zero, they did find some privilege escalation exploits from doing Rowhammer style attacks. So it's a very serious, very real attack that RAM manufacturers, DRAM manufacturers have to be aware of. So I want to go back to this slide for one final point on what the quantum runtime looks like now, and how it's distinct from classical runtimes. We are CPU. We have our motherboard. We have our runtime. We have our access layer. There is a stack, and that's it. We pop off the top of the stack, and we run the instructions off the stack. There is no syscalls. There is no root user. There is no user space, really. You have the entire run of the machine as a user, and we just pop your instructions off the stack and execute them. A very, very simple runtime right now. It also lives for 0.2 seconds, and then the entire system shuts down, effectively. At least from a data perspective. This whole thing, we kept our fridge cold for 18 months. So we had an 18-month continuously running quantum computer, which was a record at the time, proving that cryogenics is not problematic. And so these are the differences. We don't have any of the subtleties that you have to deal with when separating out root access, system calls, all these passwords, environment variables. We have none of that. We have a set of numerical instructions we pop and execute. But there's still space for things to go wrong in this very simple execution model. So this is quantum-ish Rowhammer, or quantum Rowhammer-ish. So that computation that we were examining earlier, this 2-bit computation. Let's say Alice wants to run this. So we assign Alice qubits 1 and 2. You can run there, that's fine. But we've got 6 other qubits sat idle. That's lost revenue. You know, we could be doing even more throughput. And so if Eve comes in and says, I've got a 2-bit operation as well, let's put Eve here. Because this maximizes the remaining possible qubits for even more users to get involved. And this is a piece of chasm. This is a textual representation of the computation we showed before. This is the Hadamard for qubit 1, and this is the CX gate for qubits 1 and 2. And this is the output. There's a little bit of noise, right? These machines aren't perfect, they're a bit noisy. But 1, 1, 0, 0 being our most probable outcome. So let's flip back quickly to here and think about what might Eve do. This was a foreshadowing. What might Eve's computation look like with those 2 qubits? If you think of this as user space, qubits 1, 2. Eve doesn't need permission from Alice's user space to drive an interaction. The way that Eve drives an interaction is entirely local to Eve's user space. And so I can do that. It's come out a bit small. No, but this is an extension of Chasm called Open Pulse. And this is a language that gives pulse level access to users. So what is the program that Eve is running here? It's exactly what we looked at previously, which is Eve says, okay, I'm going to drive qubit 8, but not the usual frequency, not the usual energy. I want to drive it at qubit 1. And it's destroyed the results. This is what it should look like. This is what we get afterwards. It's a mess. It's garbage. It's garbage. It's useless. But what's hard about this is that the point of open polls is to give researchers access to do things like sweep through frequency. So it's a perfectly normal request to make. It doesn't look malicious unless Eve's in a particular space. So that's our little demonstration of a classically inspired quantum Rowhammer. We're able to destroy the results of another user without having to access their user space. How do we remediate for this? Sorry, question.
No, exactly. That was my question. How do you remediate?
Yeah.
Coming up soon.
Yeah. So, in a lot of superconducting devices, architectures like Rigetti's until this week, and like ours, like IBM's, these are fixed. These couplers are there, they're in place, you don't get rid of them. So we just have to move Eve. There is no way that I'm aware of. If there is, let's think about it. We want to maximize usage. You just have to move Eve sufficiently far that she can't drive an interaction through many qubits. So you would just have to say, unless I can situate you sufficiently far, I can't thread this execution. There are other architectures that come with additional complexity with manufacturing, where you can tune these couplers. You can turn them on and off, basically. But it's much harder to manufacture them and calibrate them. But that would allow you to start really packing in the possible simultaneous users. Yeah.
Is there a reason why you didn't move E space to 7.6?
Yeah. You could. But if I was to genuinely implement this within our runtime, I would put them as distant as I can. Because I genuinely don't know that there isn't a way for Eve to drive a multiple qubit interaction.
So, by that argument, is there also the progress that 5, 6, and 7
Yeah, maybe.
So
Yeah.
it's real simple to, based on Harlequin computing like Maniac, where they actually had to shift circuits or conductive devices at a right angle instead of at a direct angle. Otherwise, it would actually influence the power surge into other coils around.
Yeah.
So this is feeling very early computing, but it'll go faster.
Precisely. And I love that's precisely what I was trying to get forward in this. In fact, the ENIAC is probably a bit advanced. We're barely at like ticker tape type machines, but this is exact. And there is more subtlety here as well, because I've laid this out in a ring. Physically, this isn't how it's laid out. Some of these qubits are like pulled in slightly closer to one another, and so there is this like parasitic coupling you can get just by proximity. So things like the end, moving couplers at 90 degrees or whatever you want to do to try and shoot any stray fields out into the ether. Absolutely. Any more questions before we move on? Yeah.
Can you just keep entangling them to get back to 7?
Maybe. So one thing you can do in the middle with these qubits, you could apply some decoupling regime. In fact, you can drive the other qubits very, very hard and try to block out other interactions. Or just keep measuring qubits in the middle to stop interactions happening. But this is what I'd like to work out precisely. I'm speculating here. We I don't know the best way to remediate against this problem. Yeah.
So when you said they were offset, is that for security reasons, so we're trying to do like a deep cleans just for the problem?
Yeah, something like that. Something like the aqueous chest problem is very analogous. You want to remove any direct lines of contact with these things. That's a very good way to put it. Oh yeah, go ahead.
You said there was some noise issue when they were close together as well.
Yeah.
Is there like a level of frequency that you can just cut off and say capacities?
Yeah, exactly. So it's hard because I can cut off frequencies to prevent like malicious exploration, but I have to allow the malicious frequencies because that's how a regular computation is done as well. So I can block particular frequencies on qubit 8 while something's running here, but that would limit the open pulse interface would become limited, which is fine. Open pulse is very hard to use as well. Like not many people use it, but yeah, blocking frequencies, hard blocking frequencies, could be a good way to do it. Absolutely. Go
In
on.
a similar vein, with making it sort of polyphasic, so you have different phases, shifting the phase around, or does that not actually have any effect in mitigating it?
I don't think so.
Okay.
I don't know. Let's try it. Basically, the answer to almost every question is let's try it.
Do you think the phases that sounds a bit slow?
No, our phase shifts are instantaneous. They're done in software. Yeah. So if you have a rotation, like you have your vector here, instead of physically driving a phase change, you change bases. It's virtual. So phase shifts are free.
Sorted.
Yeah, sorted. Cool. Any more questions? Loving this. Thank you, everyone.
What's your stability as far as your microwave signals that you're using?
I don't know.
I'm only asking that because you have influence of things around us.
Yeah.
You know, solar flares, things like that. They
Yeah.
actually can impact a computing device like this if it's not shielded, but you know, it has to be really safe.
Yeah, absolutely. There was a paper from Google where they started to do some error correction experiments that implied that these solar flare, these solar events, were a limiting factor for how good their machine was. Yeah, if we get hit by some solar flare here, the whole thing it gets excited. It adds enough energy to drive the whole system into 1 or higher. So I said, I look like these were bits. Really, these are very high dimensional systems.
Well, we happen to have that relation.
Yeah. It's a problem for distributed HPC clusters as well. Bit flips somewhere here, and your MPI whole node goes down. So we stick them in a lead-lined room in Colorado or something. Yeah.
Talking about this, then you talk about large frequency changes, so is this
Yeah. So let's say it's analog. You can stick to the subset. Classical compute, reversible classical compute, is a subset of these quantum algorithms. So it's a generalization of classical compute to a probability theory sense of doing it. So you move away from just 0 and 1, which you can do. You could just do classical, like the not and the conditional not, and just do classical compute. You could build an adder quite easily. But we also have the possibility of adding these superpositions where you become analog. Yeah.
Each qubit is driven by their own antenna or doesn't share the other?
Yeah, so currently each one of these has their own microwave control line. You can like multiplex, you could send multiple tones down one drive line if you wish to. But most people tend to have one drive line per qubit. Say again?
That's precise enough.
Yes. Yeah. So in fact, our qubits are actually tiny, nanoscale fabrication. This is the size of this antenna is basically the size of the coax at the bottom to pick up and couple towards that microwave driver. Sorry, say again?
The activity is a charge of the antenna, the power from each other that you can change the antenna.
Yeah. And so this is the part of the core IP of OQC, is what's called the coaxial. If you are familiar with the transmon technology that many superconducting devices use, you have your control lines come in plane, and you have to solder them in, you have a flip chip to get it over. Our control lines come in perpendicular to the device and are air gapped. So there's a sample package holder, you just screw your control lines into the top, and it's lined up to the qubits underneath. If it goes wrong, there's air gapped. You flick out the dud one and you put a new one in. Yeah. Sorry, say again? How many values? So like, yes. So it's a continuous spectrum. So you have zero. It's a sphere because you also have a phase. So you go zero anywhere between 0 and 1. So 0 plus 1, and then you can travel across the equator as well. Yeah.
What's your qubit resolution around that rotation?
Good.
Magnificent.
Yeah. Perfect. Yeah,
Brilliant.
yeah. I couldn't say off the top of my head what our like angle of resolution
Just
is,
curious.
but phase is perfect. Let's keep going back to phase. Yeah.
So you said you keep just excite the qubit and then you keep the phase in software, right?
Yes.
Between these links, could you put a diode that is controlled by software that allows or doesn't allow a current to pass through?
So that's something like the idea of these tunable couplers, that you can shift these couplers very far out of the coupling space. So yeah, this is basically what people like Google do, and Rigetti as of last week, these tunable couplers. Typically that's mediated by a magnetic field that kind of switches these things on and off. Yeah, that's absolutely what some people do.
So I think if you can control that, then maybe by tracking which bases are in the next few weeks, you can schedule it in to not be in a singular basis that would allow software bases that would allow your negative to expand.
Yeah.
But you need an eye and see that the bases either allow the
Yep. Yeah, absolutely. And that's a challenging software and engineering problem to build in conjunction, but a very good solution. Oh, sorry. Yeah, go ahead.
When you said that you're qubit that are hearing learned that my energy from interface to other interfaces being brought outside that qubit.
Yes, absolutely. Yeah. So this is one way to drive a two-qubit interaction, is the way I've described it. There are many, many other ways that involve pumping into these higher energy states. So you can do the same thing, go higher, and then, I'm not going to enumerate all the different possible ways to drive a two-bit interaction. It's basically continuous, how the number of possibilities of that. Yeah, precisely. I think I'm going to move on to the next slide.
I was gonna say it.
Slide in. Sorry.
I just want to throw this slide up to shout out some amazing researchers. This review of primer and security of quantum computing. This is starting to be seriously considered by many different researchers. Farouk Sonash and Abdullah, IBM and Penn State, respectively. These folks are taking this very, very seriously, and there's not a huge body of work compared with like the body of work in hardware, the body of work in algorithms, but it's starting to get there and being taken seriously. As the computers get good enough and sophisticated enough that we can start to think about these sorts of threaded execution models. But you can see that this isn't just quantum. There's scheduler attacks. Everyone has a cloud API, right? There's a whole bunch of just classical security engineering that can leak things in unique ways in the quantum space. Yeah, this is. We'll make these slides available so people can get these sources. But I'll say this is probably the best or the only review in the space of quantum security experts. So, quick fire. I've got plenty of time, for any more questions. Quick fire, these are just some ideas to get people thinking about all the different things that might happen, inspired by different classical software exploits. Overflow inspired. What happens if I ask for a number of measurements? What happens if I ask for 0 measurements, or -1 measurements, or 2 to the n plus 1 measurements? This is all custom built. All this stuff is custom built. We're going to rediscover a load of overflow attacks. Yeah. Woo! We talk about open pulse very, very loosely. Open pulse lets users define these microwave envelopes that get sent to the quantum computer. What happens if I ask for a massive pulse, a massive voltage, and you can put arbitrary times. I want your maximum voltage for 3 days, please. And let's heat that fridge up. And a slightly more subtle one. Qubit used after free. This was a suggestion from Quantum Village organizers. This is a different language spec, QIR, Quantum Intermediate Representation. For any Clang users, for any LLVM users, this is an extension of LLVM intermediate representation that includes quantum elements, so that we can distribute our compute. You can parse them with CUDA to do some GPU acceleration. You can also throw in that quantum element. And the CUDA quantum project from NVIDIA is doing precisely this. But what have we got here? We've got an allocation and a release. I mean, that's, used after free. This is a problem classically, and we're rediscovering it. And just gives a sense of why would you do this. There's a lot of algorithms that temporarily require entanglement to other qubits to perform a computation, and then they don't care. But there's information still in those qubits after they've been released. So I could jump in and just measure them, and extract some information out of the system. But we've got side channel attacks. Look at all these lovely labs. Look at all those lovely wires in free space and the LEDs that are blinking. Right, that looks like side channel attack vector space to me. Maybe you can tell me I'm wrong, but there's lots of resistive heating, there's LEDs, there's lots of ways that information will be leaked. Right now it's not, because of where these machines are situated, that's not a problem. When they start going out, when they start being openly sold to anywhere that isn't a very secure environment, this becomes a problem. And it's something, again, you see we take very seriously. Our future deployments are taking place in data centers, are very, very secure environments, classically speaking already.
What is the variance as far as from the power standpoint?
Not very, very low power variance.
Yeah, because that historically was a real problem over the years.
Yeah.
Mainframes and mini computers.
Yep.
They had better variability on the 60 hertz or the voltage itself, and that actually caused major havoc, including rewriting registers and everything else.
Yeah, I agree. It's something to explore and understand. How much is that, and will that affect us as well?
Try it on your system.
No. Hysteresis. Sorry, there was a better name I was given about this. To prove I'm not a security person. When you delete something on a memory stick and it's not deleted, it's still there. Whatever that's called, whatever that exploit is, we have a quantum version. So what happens when this is now threading not on a QPU, but shot to shot. So every measurement I flick between a different user. Something like a fair scheduler in a kernel. Right? We're flipping between these different bits. if I'm in state 1, realize that we're adding energy into the system. So this is a higher energy level that has to relax back down to 0 in order to be safe for reuse. And it's an exponential decay, which is quick, but that's still not 0. So this is a setup problem that might go wrong. In that if I don't leave enough time between the shots, there's information still lingering in the system about who was previously running on the device. So Alice's shot, this might be genuine. This is trying to do something good for the world. Eve just comes in and said, I'm just going to measure. I'm not going to do any computation, I'm just going to measure. And if Alice is trying to generate cryptographic keys, I'm just going to measure those keys. So this is something that our remediation is for. So a good active reset, where we pump the entropy out the system and make sure we're at 0. Yeah.
The x-axis on your graph, is that 8 times 10 to the negative 5, or is that like 8 times 10 to the negative 6, and then the end of the graph is 1e negative 5?
This is, yeah, the whole thing is multiplied by 1e minus 5.
Okay, great.
And this is real, it's T1 it's called, which is the relaxation energy. This is genuine data that we collected. I don't have it particularly, but this is what, these characteristics are very well understood in the physics space. Yeah.
This actually is directly looking at it, very similar to magnetic memory that was used in the Apollo and the 60s.
It is. It's exactly like that, where you have this dissipation of the energy that happens over some time period. Yeah.
It's very good based on all the other cells.
Exactly. Every qubit will have a different, we call it T1 time. This one has a T1 time of 22.5 microseconds. Every qubit, they'll range, I think we're up to maybe 200 microseconds. In the industry, that is, 200, 250 microseconds. Like Google get away with very low, they have like 30 microseconds. So there's a huge variation on what these relaxation times are. Timing attacks. Any crypto engineers here who doesn't love a timing attack? These 2 qubit gates that I mentioned, they're not as simple as just drive it for 100 nanoseconds. They vary a lot. The calibration doesn't just check for the frequency, but it also does the amplitude, the length of time it takes. So here, this is the IBM Auckland device, and their range is 284 nanoseconds and 746 nanoseconds, where each 2 qubit interaction varies between those 2 extremes. So what that means is you can get some information about the structure of the circuit just based on how long it took or didn't take. Oh, a remediation for this is you make all your gates the same length as the longest one, right? You add a delay in. Then maybe there's side channels there again. So now that was all the bad news, all the ways it's going to go wrong. The last 2 slides I have are about some mitigations. This first one, blind computation. This is some work from Anne Broadbent, Joe Fitzsimmons, and Elham Kashefi, 3 astonishing researchers that were very, very pioneering in understanding the links between quantum computing and cryptography, and how they can really help one another. I'll briefly, what's this cluster? So this is a new model, what we call measurement-based quantum computing. I'm going to brush over exactly the details. But what we do here, previously, when someone asked for a 2-bit operation, we did that for them. In this model, we preload all of the possible 2-bit interactions. So we entangle our entire system, and then the way we do compute is just by doing measurements sequentially on individual qubits. And the angle of those measurements changes the computation. Why is that important? This is client stuff. This is classical verification prover stuff. Oracle improvers, all that cryptography theory. I have some computation that I want to perform that I can represent. Basically, it's a series of angles, of very particular angles, not just arbitrary. what I do, the client, if I don't trust some machine, I inject a state into that machine that kicks off the whole thing. What that does is it gives me a one-time pad. I've encrypted my entire computation in the combination of angles and this injected state. So if I interleave my computations with genuine compute and trap compute that I know the answer for by just doing 1 plus 1, it's normally something more interesting than that, but encrypted 1 plus 1, then I can tell I'm being fooled here because my trap computes keep coming back wrong. But because it's one-time padded, the server has no way of telling the difference between the trap and the genuine. And so it's impossible to, theoretically of course, impossible for the server to trick you and pass the traps and fail the genuine ones. So this gives us assurance. It won't necessarily fix it, but it will tell you if you're being tampered with or not. And in fact, in an incredible, very recent paper, they actually physically implemented this. Some really astonishing work. This has been decades of work to get to the point where they've actually done this. It's something that's very easy or hard, depending on your architecture. So to talk earlier from Xanadu, for photonic devices, this is easy. You just stick a fiber optic cable into the front of your device, and you give me the other end, and I inject my states. Equally, some ion trap devices is quite easy to do. It is quite hard to do for superconducting-based devices, but there are proposals if you're working towards something like that. Yes. But just a sidebar, this isn't just for detecting if I'm being messed with. It also tells me that my device is running correctly. When I get to the point where I cannot verify the correctness of my answer, it's not MP, I can't check it polynomial time, then I can use this method to say, yeah, your device is running well, so you can probably trust your answer. And the final mitigation is error correction. And this is RAM manufacturers bake error correction into their devices for very similar purposes. Well, there's a few reasons we do error correction. But let's take a classical error correcting code. We take any time I see a 0, I make that 3 zeros. Anytime I see a 1, I make that 3 1s. And then when I take a measurement, I take a majority vote and assume that approximately 1 error occurs. That's the simplest possible error correcting classical code. The difference with quantum compute is that we have 2 errors to correct for. We have this 0-1 error, this bit flip error, where I said we also can traverse the equator between 0 and 1. So in this sense, we have a phase error as well. I can go from 0 plus 1 to minus 1. So basically, there's 2 equators I could bounce between. And so we have to bake 2 errors into our error correction. This is a recent paper from Google demonstrating the phase flip and the bit flip error, demonstrating that you can correct these things. And this is what people talk about when they say fault-tolerant quantum computers. It means that you are correcting for errors faster than they're occurring. And this could include malicious errors. This is a surface code, this is cool. They're not very good at highly correlated errors. So it's still not very good if you get hit by a cosmic ray. You still die. There's not much you can do about that. But this is somewhat the end goal of quantum computing. And when we have full error correction, that's when you have to worry about things like Shor's algorithm and your cryptography. Current estimates maybe 20 million qubits to crack RSA 2048, I think. Don't quote me on that. We can Google it afterwards together. Yeah, so this is will really solve most of the problems. Not the side channels, of course. Side channels are always there. Timing attacks will still be there. But malicious intent we can correct for.
Another weird question. So are we looking at this only in 2 space? Or are we actually looking at it in 3 space? Are you actually using something like this crystal type furniture?
So this surface code is based off a torus, and you have one direction goes one way and the other goes the other way, and it adds a lot of redundancy. into your system. But the basic idea of error correction is you add redundancy into your system such that if a few bits go wrong, you can detect that and correct it. Same as classical and quantum. And this is my last slide, so any questions? Go there now. No. I put my email down here. I'd love to hear any of your ideas, any suggestions. I want to get this conversation going between the quantum and the hardware hackers and the regular hackers. I want to get our devices as secure as possible. And so please give me an email, jfriel, Friel, @quantumcircuits.com, and let's talk hardware hacking. Thank you for listening.
Woo!